Next speaker, Manki. Thank you for coming.
Thank you very much for the invitation to speak. It's been a real pleasure to attend an in-person conference and to talk with people in real three-dimensional space. So this has been a great pleasure so far. Today, I'll talk about new tools for analyzing non-perturbative superpotentials in 4D string vacua. This is based on there we go. This is based on recent work that appeared on the archive with Manki Kim, who's in the audience, and also on some loosely on work that's also in progress with Manki, and that we hope to have appear on the archive sometime in the near future. So what I'll talk about today is a problem that is motivated and inspired and very concretely by the aspirations to construct KKLT-like vacua. And it's essentially a problem that's focused on a particular aspect of those constructions, which is Kähler moduli stabilization. The setting I'm working with is it's type 2B string theory compactified on Calabi-Yau 3 orientifolds. And the idea in these setups is that you have a laundry list of requirements that have to be satisfied. For instance, one of the requirements is to have a small classical flux superpotential. Another requirement is to ensure that the F terms for Kähler moduli vanish and that the perturbative expansion in alpha prime and G string are well controlled. And yet a third requirement, and the one that I'll focus on today, is that there is a non-perturbative superpotential that's generated, which contains enough terms to stabilize the Kähler moduli that are visible in the compactification. So a leading order, one can expect the superpotential to take the following form. And this is a schematic expression for the non-perturbatively generated superpotential. It depends on, well, the sum depends on some choices of divisors that I denote by this d hat. These are prime toric divisors inside of the Calabi-Yau 3 orientifold. Here you have the so-called Pfaffian prefactor, and then there's some exponential dependence on the complexified volume of these guys. So one of the issues that complicates understanding this object in detail is the moduli dependence. Here, Z is a complex structure modulus. Tau is the axial dilaton. And in general, the moduli dependence of these contributions is not well understood. It's a challenging mathematical problem that remains open. But there is a simplification that can be made, namely to find situations where this Pfaffian prefactor is constant and non-zero. And so this is the simplification that I'll be focusing on today. If these requirements can be satisfied, then it's possible, people have shown, especially according to recent work, that it is possible to find small classical flux superpotential, and in the process stabilize moduli at large Einstein volumes, so you get some sort of expression like this, looking for a minimum. But one of the trade-offs for doing this sort of thing is that in practice, these small values have to be found for computational reasons. They're most easily found at small h21, and it becomes a very computationally challenging problem to find them for large h21. I think this is the third time you're seeing this shield diagram today. So if you recall the sort of distribution of Calabi-Yau threefolds with regards to their Hodge numbers, small h21 implies that we're going to have to work at rather large h11. And so if that's the case, then it becomes necessary to generate a lot of different non-perturbative superpotential terms. And so this motivates having some sort of control over their geometry and their physics, and basically being able to say concretely when such terms are generated for Calabi-Yau, which have lots of possibilities for generating such terms. So I'm going to work in the following situation, and this is again motivated by KKLT-like vacua, but it's by no means restricted to it. I'll assume that there are no space-time filling D3 branes, and I'll consider a so-called vertical divisor. So this divisor D bar is the thing that I get by taking the F theory lift of the Calabi-Yau 3 orientifold. And this D bar you can think of as some elliptically fibered, generically it will be some sort of elliptically fibered elliptic fibration that projects down to my divisor D hat through the projection associated to the F theory elliptic vibration. And in these cases, it was shown back in the 90s by work due to Witten that these Pfaffian prefactors, the things that we're sort of we would like to be able to ensure a constant and non-zero for the purpose of Kähler moduli stabilization, or holomorphic sections of a line bundle L, where the first Chern class of the line bundle is equal to something called the principal polarization of this object called the intermediate Jacobian. And it's defined as follows. So you can think of this as some sort of a generalization of a torus in some sense, the quotient on a lattice, very roughly speaking, and by a lattice, I mean. And while the details of this structure won't be too important for the remainder of the talk, one thing that's going to be useful is to notice that the dimension of this thing is equal to a sum over Hodge numbers. And when the dimension is equal to 0, it turns out that this is sufficient to ensure that the Pfaffian prefactors are constant. So we can sidestep this open problem of understanding the moduli dependence by focusing on situations where we know that the moduli dependence trivializes. Sorry, could you say again? The fluxes I'll assume are switched off for now. I'll consider a case of a smooth fourfold, working in the in-theory picture, but I have in mind is the F-theory limit eventually. Yeah, so I'll get to that. But. So in any case, this indicates, it motivates us to try and understand, have some method for understanding the Hodge structure of these vertical divisors in more detail. So let me give a quick summary of the results that I'll talk about today. What I'm going to present are a combinatorial formula for the Hodge numbers of vertical divisors, focusing on the rigid case. The rigid case is the case where the Hodge numbers take the following form. And this is of interest for applications because this has been shown to be sufficient to generate a non-perturbative contribution to the superpotential. This essentially is a condition on the number of fermion zero modes that live on the world volume of Euclidean M5 branes wrapping these guys. Something that's very nice about these formulae are that they only depend on the geometric data of the Calabi-Yau orientifold. So in particular, what they depend on are the equivariant Hodge numbers, meaning the Hodge numbers defined with respect to, choice of orientifold involution in mind. And the plus and the minus indicate whether these Hodge numbers correspond to the subgroups of cohomology that are either positive, they have eigenvalue plus or minus under the orientifold involution. So it depends on this as input. It depends on a collection of divisors in the Calabi-Yau 3 orientifold. So the D hat, obviously, where the places where my instantons and the type 2B frame where the instantons will be localized, D3 instantons, or where 7 branes can, the location of 7 branes that on which there can be gaugino condensation generating non-perturbative superpotential contributions. So it'll depend on the classes of these divisors, on 7 brane divisors, and on the anti-canonical divisor. And finally, it depends on, these formula depend on the number of O3 planes, which correspond to terminal Z2 singularities in the F-theory background. So what's nice about this is that it does not require an explicit construction of the full F-theory Calabi-Yau 4 uplift. And this allows us to bypass a lot of the difficulty, the pain, and the suffering that comes along with constructing these F-theory uplifts and as complete intersections inside of toric spaces, for example. So let me give a few comments on the results before I jump into the details. One comment is that the Hodge numbers, so these guys, the equivariant Hodge numbers that are denoted by these symbols here, these are essentially derived by studying the stratification of the Calabi-Yau 3 orientifold, which is an orientifold of a toric hypersurface, combined with an action, understanding the action of the orientifold involution. The dependence on the divisor classes that I alluded to in the previous slide, and also the number of O3 planes, this is fixed using a conjectured expression for the Euler characteristic. So this is, obviously the standard expression for the Euler character. There's nothing new here. The conjecture comes about by the observation or really the suggestion that to get the correct expression for the Euler character, we should not only integrate the third Chern class over the volume of vertical divisors, we should also add to it a correction term, which accounts for the contributions of O3 planes. And this is important because perturbative O3 planes are actually rather prevalent in F-theory models with a global sin limit, which are suitable for studying type 2b Calabi-Yau orientifold compactifications. So these are sort of a ubiquitous feature that one can't avoid, and it's necessary to have some sort of expression for the purposes of our formula that compute the Hodge numbers that accounts for the possibility of these things being, these physical objects being in the background. And the final comment I'd like to make is that we do a cross-check of this formula. There's actually two types of cross-checks. One of the cross-checks is computing Hodge numbers from something called Hodge-Deligne numbers, which I'll speak about in more detail in a few slides from now. And this is done in known F-theory uplifts, where we actually know what the full elliptic Calabi-Yau fourfold construction is, and we can sort of compute things by hand as a cross-check. And the other type of cross-check we do is comes in the form of the heuristic general arguments that are done using local geometric models. So this doesn't constitute a full proof of this conjectured formula, but it does constitute what we believe is pretty strong evidence, and hopefully a solid proof of this is forthcoming. So I'll talk about this again later. So the plan for the rest of the talk, in view of time, is to sketch first off a derivation of the formula that we derive. Then I'll talk about these cross-checks with particular focus on the local heuristic arguments in the context of local geometric models. And then I'll end with some conclusions and comments about future directions that we're currently pursuing. Okay, so let me set the stage. I'll be thinking about, first off, sort of the starting point, the motivating starting point here is type 2b on a coordinate flip Calabi-Yau 3 orientifold. So I'll start out with a Calabi-Yau threefold that I realized as a toric hypersurface of some toric space, which I denote by B4. And given a choice of orientifold involution I, I'll use something called the refinement map to define a related space, toric space again, B4 hat. And the Calabi-Yau 3 orientifold will be a hypersurface inside of this toric space, which is related to the original toric space by this thing called the refinement map. So in these setups, I'll expect to have three types of extended charged objects inside of the Calabi-Yau 3 orientifold. These are going to, for situations where I hope to be able to think about lifting to F theory and ensuring that there exists a sin limit, a global sin limit. I'll consider O3 and O7 planes that come from the orientifold action, and also stacks of 7 branes that can carry an SO8 gauge bundle. So an example of an orientifold, which has been well known and studied, I think, rather extensively, dating back many years and to some early string theory literature, is an orientifold of the quintic threefold. So the quintic, which you've heard about a few times today, is a degree 5 hypersurface inside of P4. If we restrict to a Z2 symmetric point and complex structure, we can define an orientifold action, which sends the first. So I have 5 homogeneous coordinates here, x1 through x5 for P4. And the orientifold action, which is an action that I define on the toric space, which restricts to the hypersurface, the quintic hypersurface, is an action on x1. It sends it to minus x1 and keeps everything else stable. This is a particular realization of this orientifold involution. And here I've presented the quintic as in the language of gauge linear sigma models, GLSM. So this is the usual description that one sees of the ambient space. And then I've included also the extra term that appears in the superpotential. And then here I have a new space, which is a weighted projective space. And inside of this space, the associated degree 5 hypersurface is going to be the orientifold of the quintic. So within this, there's 2 fixed loci of interest. There's an O7 plane located at x1 is equal to 0, and then there's an O3 plane at x2 equals to x3 equals x4 equals 5 equals 0. So that's the base of the F theory elliptic fibration that I'll consider. And over this, I'll define an F theory fourfold, an elliptic fold bone elliptic fibration. At least conceptually, I'll think of one being there. So I have in mind some sort of F theory uplift where now there's an elliptic fiber which generates in the the vicinity of the 7-brane locus to the D4 extended D4 Dinkin diagram. And an example of an uplift of an orientifold, which is was studied, I think, first written down explicitly by Colanucci, but maybe some aspects of it appeared in earlier papers, can be represented as follows. So this is the ambient space of the in the GLSM description, and then there's some Weierstrass model that's defined as well, this should really be thought of as a complete intersection. There's a Weierstrass model, and then within the base, obviously, there's going to be, the base should be thought of as a hypersurface of the weighted projective space, defining the orientifold quintic that I discussed back here. So within this F-theory uplift, what I'll think about is a vertical divisor. So imagine I look at the Calabi-Yau 3 orientifold base, and I select some prime divisor that I denote by d hat. This is represented by this blue line. And then I think about lifting this through the F-theory construction to some elliptically, generically, I might see something like an elliptically fibered divisor inside of a Calabi-Yau fourfold. So that this is what I denote by d bar. And this sort of sets the stage geometrically, and now I can talk about the various ingredients that go into deriving formula for the Hodge numbers. The first ingredient is having some method to compute the equivariant Hodge numbers. So there's two pieces of key data here. One piece of data is the so-called refinement map, which allows me to map from, if I take the inverse of this, it allows me to map from the Calabi-Yau threefold to its orientifold. And the second piece of data is something called stratification. So for those of you who are familiar with projective spaces, for example, these emit stratifications. A stratification is simply you can think of it as a decomposition of a projective space, or more generally a toric, projective toric variety, into a disjoint union of different subsets, which look like algebraic tori. So here's a simple example of P1. I can think of it as 2 points, disjoint union of 2 points with the algebraic torus C star. So toric spaces emit stratifications. They can be written as these disjoint unions of different subsets, which are built out of algebraic tori and sometimes some exceptional spaces that come from doing blowups. And similarly, for nice constructions of Calabi-Yau hypersurfaces, you get a restriction of the stratification of the toric ambient space to a stratification of the Calabi-Yau hypersurface. And similar, the same structure, an analogous structure, maps through the refinement map to the orientifold, and it also restricts in favorable cases to constrain and describe the topology of the divisors in which we'll be interested. So the stratification is particularly nice for computing Hodge numbers because we can use something called Hodge-Deligne numbers, which are defined as follows. These are defined as signed linear combinations of Hodge numbers defined with respect to cohomology with compact support. And from these, I can define a so-called Hodge-Deligne character. And the beauty of these objects is that they're additive over disjoint unions and they're multiplicative over products. And so they play nicely with stratifications of these different spaces, and therefore it becomes very easy to compute them in examples of interest. So this gives a very nice concrete way to compute the Hodge numbers, equivariant Hodge numbers. And there are, in the paper, there are some very nice novel formula that tell you how to take the toric data defining these various objects, and from them extract the different Hodge numbers. And this is one of the results on which the eventual result will be built. So importantly, the cohomology, I think I've mentioned that it splits into eigenspaces under the orientifold involution, and it's the plus eigenspace that will tell us something about the Hodge numbers of the divisor d hat inside of the Calabi-Yau orientifold. Okay, the second ingredient is understanding the anatomy of vertical divisors. So what I talked about on the previous slide, if I go back to my original picture, was thinking about some prime toric divisor inside of the my Calabi-Yau 3 orientifold. I'm looking for divisors on which I can wrap, for example, Euclidean D3 branes that will generate a non-perturbative superpotential. So these divisors have to be rigid in an appropriate sense, and that's the case that I'm focusing on. And the question is now, once I lift this rigid divisor, prime torque divisor, through the some F3 elliptic vibration, is there a way of sort of classifying or characterizing the different possibilities that I'll encounter? So that's the second ingredient. And the first thing to notice here, without actually going through the trouble of building the entire elliptic Calabi-Yau, is that the defining data that goes into the elliptic Calabi-Yau, the fourfold F-theory uplift, in principle, is a choice of twisting line bundle. So this is going to be the anti-canonical bundle of the Calabi-Yau 3 orientifold. And there's a way that we can use this data to restrict it to the geometry of the vertical divisor to get a sense of the different possibilities. And this is using the way this is done is we use something called the Itaka dimension, which I won't. I'll give a flavor for what it does, but I won't define it in great detail. But suffice it to say that if we understand the Itaka dimension of this line bundle restricted to my prime torque divisor inside of the Calabi-Yau 3 orientifold, this gives enough information to sort of map out the different possibilities for what sorts of vertical divisors we'll find. So just to focus on two aspects of this mathematical object, the Itaka dimension, which I denote by dim, it's not literally the dimension of the line bundle, but it's sort of I'm using an abusive notation here. This is something that ranges from -infinity by convention and goes all the way up to the dimension of the thing that it's defined over. And it characterizes the dimension of the subspace over which the vibration varies non-trivially. And it can be computed from toric data as the dimension of the Newton polytope corresponding to this guy, to the anti-canonical divisor class restricted to my prime toric divisor d hat. So using this sort of breakdown of different possibilities, and indeed we look at all possibilities ranging from -infinity to 2, in combination with some a bound on the Hodge numbers of the vertical divisors expressed in terms of the equivariant Hodge numbers, as well as a physical assumption about the matching of fermion zero modes, which is I list right here. It's possible to get a formula for the Hodge numbers of vertical divisors for each case, except for a single Hodge number, and that's H21. So I'll come back to this point briefly, momentarily. So the third step is to get this missing Hodge number H21, which we need to have enough information to characterize when the Pfaffian prefactor is constant. So recall that when this is constant, these are going to vanish. I'm focusing here on the rigid case, so this is assumed to, I mean, it's possible, of course, to study to recover the Hodge numbers in full generality, but I'll be particularly interested in cases where the vertical divisors are rigid, and so this guy will vanish, and the question is whether or not H21 vanishes. And the strategy for recovering this additional Hodge number that we weren't able to compute is to compute the Euler characteristic, which has this expression. So if I know H11 and I know the Euler character by some simple algebra, I can figure out what H21 is. And the way we do this, at least the first approximation, is to use the Weierstrass model data. So this is based on results of these papers, worked with Monica, who I believe is in the audience, or at least attending the conference, and also with Andrew Turner and Mboyo Asole. There are some nice formulas in these papers, in particular dating back to this paper, where it's possible to compute expressions for the Euler character of large families of Weierstrass models using push-forward techniques where the expression for the Euler characteristic is pushed down to the intersection ring of the base of the elliptic vibration. So we can apply the same thing to the elliptic vibrations that define these vertical divisors in this case. Now, the reason why there's a question mark here and why I said this is a first pass and not necessarily the full answer is because the formula have to be corrected in the presence of both 3 planes, which are terminal Z2 singularities. So the formula would be sensible formula if the base of these vertical divisors, in particular, if we think of these as elliptic vibrations, if their base was completely smooth, but in the cases of interest, it's possible for there to be terminal Z2s, and this actually changes some of the geometry and the physics in a way that has to be accounted for carefully. So we have a conjecture for the correct formula here, and it's to use this expression, which can be thought of as the integration of the top Chern class over the vertical divisor, plus a correction term that depends on the number of O3 singularities. And this passes numerous checks. So these are the 3 steps, and I just flash here a sample result without spelling out all the gory detail of the formulas. They are a bit lengthy, but they're quite nice nonetheless. So this is the case where the Itaka dimension of this line bundle restricted to d hat is equal to 2. We get nice formulae that express the Hodge numbers of the vertical divisor purely in terms of the data that defines the Calabi-Yau 3 orientifold. And it's not necessary to construct the full F-theory uplift. So let me come to the last part of my talk with the remaining time that I have left. There's 2 heuristic arguments that I want to present in the context of local geometric models. So the first model is an elliptic fibration, a local Calabi-Yau, you can think of it, that's going to be defined over a base which we conceptually imagine to have a choice of d hat, which is equal to P112. This is a weighted projective space. And this weighted projective space naturally has a Z2 singularity associated to it, an orbifold singularity. But this orbifold singularity, the important distinction here is that it doesn't always correspond to an O3 singularity. Only certain special singularities will correspond to terminal Z2 singularities. And in this case, in this choice of local model, this will depend on a particular choice of twisting line bundle that we use to define the elliptic fibration, and which restricts to the vertical divisor. So it turns out, without going through the full details of the construction, that for odd A, this is just a positive integer or non-negative integer. For twisting line bundle characterized by odd A, this H here is just a hyperplane class inside of P112. It turns out that one finds terminal singularities inside of the elliptic Calabi-Yau uplift that corresponds to the F-theory background. And indeed, in these cases, the naive formula for H21, which would come from computing the usual Euler characteristic, and the one that has the corrections, they differ, and the difference can be attributed to the number of O3 singularities. And the O3 singularities appear to be absent in these other cases. So this is one local model that sort of gives a heuristic argument for why the correction term has to be there. The second one is a local elliptic Calabi-Yau 4, which is defined as an elliptic fibration over this particular choice of base. This is a non-compact base. It's C3 mod Z2 times Z2. We can do a resolution of this, and then we can construct an orientifold from it. So this is a local CY3, and then we get a local CY3 orientifold. The orientifold, so what I've presented here actually are 2 possible different resolutions, which are related by a flop. After I do the orientifolding and subsequently lift it to the elliptic Calabi-Yau 4 uplift, the F-theory uplift, this flop lifts to a flip, actually. So it's not a flop in the traditional sense of flop transitions, but it introduces additional singularities depending on, or removes them depending on which side you're on. And in particular, one can see that for one choice of resolution, there's going to be an O3 plane generated. So there's a terminal Z2 singularity here. And we can check in this case our formula by looking at a particular divisor, this divisor E12, for example, that we compute in the process of doing the resolution, and compare the Euler character in the 2 phases. And we see that indeed in one of the 2 phases it's necessary to include the correction term. And this is precisely the phase where there's an O3 plane. So these are 2 local heuristic models. I've sort of just given a qualitative picture of what they tell us, but this is the closest we were able to get towards a proof, at least in the original work. And the hope now is to actually, in work in progress, to actually come up with a more structured and more convincing proof that is more airtight in various ways. So a few examples that are in the paper, I won't really go through them in detail in the interest of time, are listed here. So the Hodge numbers are computed for all of these examples for interesting vertical divisors in great detail. It's a very nice set of novel results, and certainly could be extended to other cases that aren't so much in lockstep with models that we expect to have applications to KKLT, like type 2D construction. So in conclusion, I've talked about derivation of combinatorial formula for the Hodge numbers of vertical divisors, focusing on the rigid case. This is the case that we know to be sufficient to generate non-perturbative superpotential contributions. These formulae, very nicely, they don't require an explicit construction of the F-theory uplift. There's immediate applications of this defining divisors that generate non-perturbative superpotential, and indeed for if you're interested in scanning over Calabi-Yau 3 orientifolds that are possible candidates for constructing KKLT like vacua, this is a very valuable tool that sidesteps a lot of the difficulty with constructing Calabi-Yau fourfold uplifts. And this also, en passant, gives new insights into stringy geometry in the presence of orientifold singularities, which may not have been pointed out so clearly in the literature previously. So future directions, there's work in progress, as I mentioned, deriving a proof of this Euler characteristic formula. It would seem that this is an example potentially of the so-called orbifold Euler characteristic, a stringy Euler characteristic that was described, I think, probably first in this paper, but and certainly has appeared in subsequent papers. This also suggests a possible modification of, maybe not a modification, modification is a bit fast, but a more detailed understanding of how to compute the Witten index for 2D sigma models when the target has these orientifold singularities involved. And possibly related to this, a modification of formula for D3 brain tadpoles, so like the Sethi-Vafa-Witten formula that appears in some of the earlier Calabi-Yau fourfold stringy literature, deriving a formula for the number for the tadpole cancellation conditions. Another obvious place that we would like to follow up on, which is this is more aspirational, is understanding the moduli dependence of the Pfaffian prefactor in detail. This is an important problem and may benefit from some of the insights that came from this project. There's a question of studying F theory with more general orientifolds. So in the discussion today, I focused on perturbative orientifolds that correspond to terminal Z2 singularities, but indeed there's other possibilities. And Yaki has written some papers about these things in connection to, I think, n=3 supersymmetry. So you can have orientifolds that correspond to non-perturbative O3 planes that correspond to ZK singularities with k=3, 4, and 6, if I recall correctly. There's also a question of defining a heterotic dual description of some of the formulas that were derived today. And then finally, it would be very interesting in the future at some point to be able to have a systematic way of constructing uplifts, Calabi-Yau fourfold uplifts, like the full F theory uplifts of these elliptic Calabi-Yau fourfolds. And this presumably for the cases of complete intersections of toric spaces would require the generalization of available technology that allows us to compute the resolutions of singular toric hypersurfaces and complete intersections to Vex triangulation. So this is also an interesting open direction that would be extremely useful, but for now, it's at least satisfying that we have some formulas that allow us to sidestep the lack of technology here. So I think I'm out of time, and with that, I will stop. Thank you very much.
Thanks very much. So the application of the formula, the reason was already, I think we wrote with nice and certain. Where we pointed KKLT problem, KKLT construction, we actually gave a formula. I think it's similar to the formula, right? The formula we had was the Euler characteristic of the ocean is equal to the number of those three planes, Euler to the 7.
Number of O7 in that case.
Was 7, number was 3 is Euler to the ocean.
I see. So there could be maybe a natural interpretation or a generalization. I see. This is consistent with the stringy orbifold. Yeah. So we thought about this a bit. It's a little bit. I mean, I'll take a look at this paper. It's been so far unclear how to apply the stringy orbifold formula to this, but I think.
You might be high on what kind of motion?
Sorry, this is high of the divisor. Yeah, the divisor basically. So there's a threefold, and inside of the threefold, you pick a divisor that may hit some of the O3 singularities, and then you lift that to F theory. Exactly. Yeah. But there's versions of this that should apply to the full fourfold as well, for example. So there's generalizations in other situations where you could imagine applying the analog of this formula. So I think it maybe should apply. Thanks for the comment.
Hi, this a few quick questions. First one, this we did as well. I read about George Johnson that how to compute corrections to topological and the characters in case of similarities. Can you look into this here? It seemed like exactly.
Yeah. It hasn't so far. It's not clear that it's helpful, but it's some open questions that have to be answered. Yeah. So I don't know exactly how to make use of it. We've taken a look at this and it hasn't been clear how to apply or adapt those formulas to this case. But yeah, I would think so. Yeah. Well, this is a starting. You know, the hope would be then if you start including space-time filling D3s, for example, which, you know, they can complicate the picture of identifying which divisors are able to generate a non-perturbative superpotential because they can rigidify like other ones. The hope is to sort of like run the same analysis and sort of generalize it and adapt it to that situation. Exactly. Yeah, that's right.